Hi, class. Welcome to machine learning, deep learning models. So in this section, we're going to talk about a TensorFlow API that's based on Keras. So we're going to be able to classify some data from a iris data set so that we can build this neural network that classifies which of the petals do we have here in this data. So we're going to be using Keras API inside TensorFlow, and Keras is a high-level API that allows you to build and train deep learning models with much less code compared to using raw TensorFlow sessions. So this is we were able to update this session from the previous one, which was using the estimator. So this is not a new version. So this is what's actually used commonly in the as an example in the industry. Okay, so the first we're going to do is we're going to extract the data from the iris file, but in order to do that, we're going to be using TensorFlow. So it is important for us to import first. We're going to do first. We're going to import TensorFlow. Sorry, that's lowercase. TensorFlow as TF. And remember that what we're doing is we're actually importing this library, and we're gonna call it TensorFlow. So we're gonna have a short name as TF, right? So instead of writing TensorFlow the whole time, we're just gonna write TF. Makes it easier for us to use it. And then the next thing we want to do is also we want to import pandas. And so as PD. So I forgot to mention, right, for the TensorFlow, this TensorFlow is it's a library for building and training machine learning models. And for the pandas, it is a library for data manipulation and analysis. So those are the important why we want to use those ones. So the next one we want to be able to import will be we want to be able to extract, we're going to load the data. Okay, so let's load the data. So we're going to load the iris data set from the CSV file into this pandas data frame. So we're going to call it df for data frame, and we're using pandas, and so we're using data pandas read underscore CSV to be able to read from the iris.csv file. Okay. So this is so just remember that a CSV file is a comma separated values. I don't think I have it yet here, so I need to upload. So make sure that you upload that file from your Canvas. So you need that file. So let's do it right now. I'm gonna look for it, and it is somewhere in here. Here I have it downloads. Okay, I'm gonna put pause here, so don't take that much time. All right, so I'm gonna drag it, and so you want to download it from your Canvas. It's there, and then you want to drag it, just drop it right here, and just say okay. Now you can see the CSV file there. Now what we can do is we can test it. We can say df. We can do df head, and that way you can see what is on the file. So we can see df. Oh, df head. just to check it's working. And you can see right now that the data from this CSV file, and you can actually open it if you want to. You can see right here, it's defined each column as sepal length, sepal width, petal length, petal width, and target. So you have 5 different columns, and the target is what's going to help us classify it. So what we're going to do here is, so remember that this df head, what it's doing is loading the first few rows of the data set. This line does not affect the rest of your code, so it's just for us to be able to visualize it. Now we don't quite we want to be able to rename this columns. So what we're going to do the next column and the next part is to rename them. So we're going to say df dot columns, and we're going to rename them. So our goal is to have them as sepal underscore length. And so what we're going to do here is we're going to rename it each column. So we're going to say sepal underscore length. That's for the first one. And the next column will be sepal, I'm sorry, quotation, sepal underscore width. And then underscore, comma, sepal length. The next one will be petal. Sorry, my sense, yeah, sepal and then the petal. This is the petal length, petal width, and then target. Okay, so we want to run this so that we can see if it should be matching what we have here. So let's run it. And I want to see it, so I'm going to do df.head. Let's see if that changed now. And you can see now it changed from what we had before. Okay, okay, good. So we can visualize it and continue. All right, so the next part that we want to do is we want to be able to define, we're going to separate the features, which is going to be our X. So we're gonna separate all the features of our columns, like the data, into this new data frame that is going to be the X values, and the we're gonna separate the target value. So you can see here, this is going to be our X value, and this is going to be our Y value. Okay, so that's your X, that's your features, right? And the Y is the target. So that's what we want to be able to match. So like based on this information, we want to be able to get this target. Okay, so let me clear this up and continue with this part. So what we do here, I need to remove this. So what we're going to do, we're going to import our NumPy MP. And so, did we already NumPy? Did we? Yeah, NumPy. We're going to import our NumPy, and we're going to import our TensorFlow Keras utilities for the categorical part. Okay. All right. So let's start with this part. So we're going to separate the targets first. So to separate the targets, we're going to drop the target column from the feature data. So we're going to say, again, this is going to be our X. Usually we use the capital X. DF, so this is our data frame that contains everything. Right now, so far it contains everything. So what we're going to do is we're going to drop, and we can name the target, the column that we want to drop. We're going to drop the target. And we want to be able to remain on the axis. Axis equals 1. So what we're doing here is we're we want to keep this, we want this to be our X. And we want this to be our Y. So what we're going to do is we're going to drop Y. We're going to drop this column from the rest of it. It's not completely gone. So what we're doing is we're just making a copy of this data frame. We're making a copy of the whole thing. We're making a copy of the data frame with just not without the target. That's what we're doing here. And you can see now, right, if we do X dot head, we can see that now we don't have the target, which is what we wanted to. So that's going to be our X values. And not only that, right, we want to be able to then do the same thing for the Y. So the Y would be, and we're going to do lowercase for the Y. And we're going to, that's going to be our target. So df dot, and we're going to specifically say we're going to extract, specifically, no dot there. So remember, the data frame still contains everything, right? The data frame still contains all the columns, all the 5 columns, including the target. And what we're going to do, we're going to specifically say target. And so I just want to show you guys that part right now. So remember, df, this is very important that you guys understand this part. Still, that represents this. This is df. That is df. We're not, when we did this, when we did the drop, that did not modify. Does not modify. Modify, or it does not change your df. It only makes a copy of it and saves it at X. Okay, very important. So that's why we can see a graph the target at the df. So we can do y dot head, and now you can see that it just contains the target. Now you might see, you don't see anything there, but we can do maybe we can do 100. You can see that there's some of them that have ones. It's either 1 or 0. And what we're going to do right now, as you can see, is it's being a float. So what we're going to do is we're going to change it to decimals. So we're going to see apply. So just integer, sorry. We're going to make sure that it's just integer values. So we're going to do this. So apply integers. Now you can see that it's just 0 or 1. Just makes it easier for categorical purposes. So that's why we went to do. I'm gonna remove this y head because we don't need it, and just to keep our values there. Okay. So the next step we want to do is we're gonna hard code the target labels. Since this is a multi-class classification problem, we'll hard encode the target labels. So that's the next goal. All right. So what we're gonna do here, we're gonna label it Y category. So it's gonna say cat, right? Y cat, which is category. To categorical Y value to a num classes equals 3. Okay. All right, so what we're doing here is we're practically just to remind you guys here, there's three different categories for our flower. We have 0, 1, and 2 for our iris species. So we have three different species here. And so what we want to do here is what we're doing in here is we one hot encoded it. So what we're doing is we take this one hot encoding and converts a class like 2 into a 0, 0, 1. So if you see this, right, let's see this d y cat dot get uh, okay, so there you go. So it's not a data frame, so we couldn't use head. But you can see here, what this is doing is labeling classification. So what it does is that this is for category 1, or this is for 0, 1, and 2. So this is like one for one species, right? And then if you have a 0, 1, 0, that's for another species, and this will represent another species, 0, 0, 1. So what it does is you're turning it into this, instead of having uh, 0, 1, and 2 as values, we now change it into just a binary numbers, like either 1 or 0. So either you have it or not. So that kind of like gives us another opportunity to be able to uh, will be able to help us manage it for our neural network to learn multi-class classification properties using the categorical cross entropy loss. But this is just going to be helping us later on. So this right now represents 1, this represents 2, and this represents 3, or the third option, you know? Sorry, this is the 2, right? Sorry, this is the 2, 1, this is the 1 value, and this is 0. So remember, we have 0, 1, and 2. Okay. Sorry about that. This is 2. Okay. So that's practically the reason we wanted to do that. All right. So we're going to remove this. And so the next part we want to do is we're going to split the data. So we want to be able to split the data so we can train it. So what we're going to do is we're going to take 70% of the data, and it's going to go for the training, and 30% for the testing. And so we'll put it right in here. So we do need to have, did I extract it? We do have here no, that's not the test split. No, we haven't done this, we haven't imported yet. So we're gonna import, sorry, from the sklearn dot model under selection. We're gonna import the train test split. So we need this to be able to split our data. And then what we're going to do is we're going to label X train as the data that is going to be from that 70, from the whole percentage, right? The entire data that we have, 70% is going to be for training, and that's going to be our features, right? The 4 features that we have. So that's going to represent that part. And then we're going to do the X test. So you have to put them in that order. Test. So that will be the out of the 30% is going to be left is going to be stored there. And then the Y train lowercase again. It's not mandatory, but it's like the standards test. And then we're going to use the train underscore test split X. So that's going to be our input. That's where we're grabbing the value from. So that's going to be split into 70, 30. And then we're going to take the Y cat. So that's going to split that also to 70, 30 for our training and test. And then we're going to say what is going to be the test size. So that what we do is we say how much is the test size automatically, the train size will be whatever's left. Test size will be, this case will be 30%, and then we're gonna do a random state to, the reason we wanna do a random state is because we wanna make sure that the data, when it's splitted, is done randomly, like it's not affected by the previous data. So that's why we wanna be able to do a random value. And the next part will be to build the model. To build the model, we need to have TensorFlow, and again, we're going to use the TF. I think we already had it up here, so we don't need it. Let me just run this one because we need to run there. We don't need this one. We already have on the top, but sure, we can leave it there. And what we're going to do is we're going to create our model. So this is going to be a sequential neural network model. And we're gonna label it model. We're gonna start with model, and again we're gonna use the TensorFlow dot Keras sequential. And I'll explain right now why we want to use this one. And so the reason that we want to use the sequential a model is because we're gonna stack the layers on top of each other. So that is why we're gonna stack the layers on top of each other to be able to make a much. So we're gonna have multiple layers. I'll explain the layers that we have here. So let's start with this part. So let's start with the first part. So let me do the drawing. When you do a neural network model, you have well, let me do a model of this. You have a bunch of neurons, right? And this is the first layer is always the input layer. And then you have the hidden layers. And then you have other hidden layers if you want to. And then you have the output layers. So this is your hidden. And this is your output layer. So we're gonna do that right now. Now they're all connected. Imagine that this is all connected. Right. So that's all connected, like neurons, right? Connected, blah blah blah. They're all supposed to be connected. I think I might have missed some of them, but yeah, you can kind of get the idea, right? They're connected. So that's just the neural network, and so you have the input layer, the hidden layers, and the output. That's what we're gonna do right now. And what we're gonna do is we're using the sequential layer. In this case, it works that if you stack them on top of each other, it will give you a better prediction. So it just works better like that. And this is there's so many different models. There's so many different models. To know which model you need to do, there's no special formula. And right now, the way you know which model you need to do is based on the data and somebody else's have tried it. Then you want to be able to try to use kind of like the same type of models, and then modify the hyperparameters. The hyperparameters are parameters that you can modify. For example, the number of layers, the hidden layers, that is a hyperparameter because you, the human, can modify them. The learning rate, which we haven't talked about, it is also a hyperparameter. So there's many different. Also, the activation function are also considered hyperparameters. So what we're going to do the I'm gonna put the first model, the first layer, layers, dense, and this is going to contain an activation. So remember the activation function that I mentioned is going to be the, in this case, ReLU. There's so many different activation functions. Now, the reason that we use ReLU is because it provides you with a much better consistent outcome. There's other ones like ReLU, the oh man, I'm blanking on the names. All right, so here is an example. I'll show you guys. The sigmoid here is an example of different activation models. We have the sigmoid, which is popular, the 10, the ReLU, which is the one we're doing right now, the LU, the max out, leaky ReLU. This is the most strongest one. There are other ones that were not that are not anymore. They practically started with those, but now they're not using them anymore. Here's the perceptron. You can't see it very well, but the perceptron is not used anymore. Sigmoid still in some cases used, but the ReLU is practically ReLU and leaky ReLU are usually often used the most. That's an activation model, activation function. That's one of the parameters that we can use. So the activation model is used to determine if the signal is going to pass through to the next neuron. It's like your function that it's like the GAR that determines if the information is going to pass to the next neuron. It's like your thread. It has to reach a threshold point of that function. So that's practically what it does. And so and then the next one will be your input shape. So we know that we have 4 features. So this is going to be comma. This is your input layer. We have 4 features, right? We have 4 features: sepal length, sepal width, pedal length, pedal width. Okay, which is your the next one we'll do is tf.keras. I'm just gonna do the same thing. It's gonna look the same as the other ones. And this is going to contain 20 neurons. And this is going to be ReLU. There's not going to be input for this one. And this is going to be our second hidden. And then we have the next one. And this is going to be 10. Activation functions are going to be the same. The input is going to be this none. It's going to be a third. Layer. And then the last one, we have 3. So this is going to have 3 layers, nodes. And then this is we're going to change it to a soft max. Again, all this right here, determining which activation function is a try and error. You look at a model and you try different numbers here. If this is what we call your parameter, your hyperparameters, you try them until you get the best outcome. So this is for right now, most of the models that you use are like try and error. That's the way it is right now. So far, this is the only way you can actually determine that. Okay, so we created the model, and now what we're gonna do is we're gonna compile the model. So the compiled model is for optimizer. We're gonna check the loss function and evaluate the metric. So we're gonna do that. All right. We'll use Atom Optimizer and the categorical cross entropy as our loss function, since it is a multi-class and it tracks accuracy. So we're gonna do model dot compile, and then we're gonna have the optimizer. Let's go optimizer, okay, equals the atom. So that's going to be the one that we're going to be using. And then the loss is going to be equal to categorical cross. This is just the name of it, so we have to select it and write it exactly how the name of the function is. So we're going to use the categorical cross entropy, and then our metrics will be defined to be accuracy. So there's different types of it. So we're going to use the accuracy. All right, so we're going to run this and see if there's no mistakes. Now the next part will be to train it. So we're going to train the model. So the model is going to go, we're going to model, and then to train it, we use the word fit. And so we're going to pass in our train data, our Y train data, our epochs, I'll explain those parameters in a bit. We're going to do batch size equals 10, and the verbose equals 1. Right. All right, so when we train this model, we want to be able this 50 epoch. So this is easy, right? This is the data we're going to use to train the model. So we're going to get all the input, all the value from the input data. This is what we're supposed to be equal to, right? So we want to be able to train it. We're going to pass it through this neural network that we have created. And the epochs, what it means is how many times we're going to pass over the entire training set. So this is, we're going to go over 50 times over the training set. So we're gonna randomly choose the data and train the model at 50 times. We're gonna grab all the data that we have 50 times. We're gonna repeat this process 50 times. The batch size is how many samples do we contain per time that we train it. Okay, and so and then the verbose equals to 1 means that the training progress will be printed. So we'll see. So we can see here it's being trained, and you can see the accuracy value there. It's getting better. It's getting better, right? And now what we're going to do here is we want to be able to make some predictions now based on what we have trained the model. And so we're going to predict the probabilities for each class on the test data. So first we want to do y, right? So lowercase y, pred. I'm going to call it pred predictions, and then probabilities. Equals the model. It's the model dot predict. So we're going to use this model that we created. That's why this is the model that we just trained, and we're going to use it to predict. And we're going to predict from the test data. So this is the model that we just trained. This is the model that contains all the modified weight values, right? This pretended that this is the brain of somebody, right? We just trained their model, their brain. And now we're gonna see, based on the training, what is it going to predict for this specific data that we have now. So we're gonna do the prediction now. And so what we're gonna do is we're gonna convert the prediction. We're gonna calculate the prediction using the NumPy arg max. I'll explain what that means. We're gonna take the y prediction probabilities. Axis 1. I'll explain right now what that means. Y true equals np dot arg max y test axis. All right, so the argmax, so this is practically, this is not bad, right? This is just taking, we have this model, we want to see what the prediction will be now after we have trained it with this data that we have here. So what we do is here, we're going to convert the probabilities to a class prediction. So we're going to use argmax. So the argmax, we use it to convert this into a predicting class labels. And so that's how we use it. We take this argmax, I think it's a method or function, either one, and it just converts it. So it does it for both of them. So this is based on what we got, and this is what we're supposed to be true. This is what the actual value is. This is the prediction made by the model, and this is what it's supposed to be. And we want to compare those two. That's what we're going to want to be able to evaluate how good did it do. And so what we're going to do here is we're going to use this matrix, which is called the confusion matrix, and the classification report. The confusion matrix shows where the model got things right or wrong. And the classification report gives matrix for each class. Like in this case, we have the Setosa or the versicolor or the Virginica. So that's practically what it does. And so what we're going to do here is we're going to print it. So we're going to be able to see it. We don't need to write the print, but we're going to see what the confusion matrix will look like once we put this, what the true value is, what it's supposed to be versus what the prediction was. Now we can see, evaluate how good is our training model. And we're going to do that also for the classification report. Classification report. So we're going to see both of them. One is going to be the matrix, and the other one will be the classification report. You guys can see one. We can do that. Oh, I think I wrote y equals. Oh, sorry, I forgot to press play to compile that one. Now this one, and you can see it, right? So this is just how many times we got it right and how many times we got it wrong. Right? How many times did it predicted one versus the other one? So 19 works for the first petal, and then the second one predicted 13 for the wrong one. But I think this is, let's see if it does it another one. Okay, it doesn't look right. It's supposed to be 19, 13, and 13. Like 13 should be right here, not all the way here. So let's see if we make some mistake in the training. Let's see, train this model again. Maybe it changes. And let's train this again. And there you go. So this is way better, right? I think it was just a bad training there. You can see now the accuracy is 90, almost 1%, 100%. That's good. So now let's see what happens when we do the classification report. So you can see that the predictions for the one was 100%. There's different values that represent different measurements, but you can see the accuracy as well. That's 98%, which is not bad. And then for the macro average and the weighted average, that also gives you the value for those ones. So that's actually a pretty good prediction. So we just built a neural network using TensorFlow with Keras API. This you should see very high accuracy in this iris data set that we saw, starting point and working deep learning. So we just created our first deep learning model here. Again, this is just barely the surface of what deep learning models are. Technically, this is not considered a deep learning model. It is considered a deep learning model when you have a complexity that determines the features of your model. But this is what we call a neural network model. Okay, it's not a deep learning model because there's a lot more hierarchy there. Some people would categorize it yes, but some people would say no. So, but it is definitely a neural network model. Okay, so we're able to predict the accuracy on the pedals. Okay. All right, so I'll stop right here and I'll go to the next one. I'll see you guys next time.